How's it going, guys, and welcome back to another 1001 MSc online tutorial video. So my name is Brock Grant, and today we're going to be going through some example questions involving work and energy. So again, just a couple of prereqs for this module. I highly recommend that you check out Work and Energy video 1, as obviously this is what all the questions are built on. And I also recommend that you check out Forces and Newton's Law of Motion, as the method that we use to calculate those questions in terms of setting up the question and extracting all the information. We're going to be taking a very similar approach with this module. Okay, so let's get started on question 1. So during tug of war, Team A pulls on Team B by applying a force of 100 newtons to the rope. So the rope remains parallel to the ground. How much work does Team A do if they pull Team B towards them a distance of 2 meters? Okay, so we're given a force, we're told that the rope remains parallel, so that's good, and we're asking how much work. So remember, work is equal to force cos theta times the displacement. So again, I'm going to start off by drawing a diagram. So we can see here we've got our Team A that's pulling on Team B by 1100 newtons. So what we do is we just fill in our equations. So work is equal to the force, which is 1100 newtons, cos theta, so this is at 0 degrees. Why? Because it's at parallel. So we don't worry about this part here because there is no angle. So we multiply it by the displacement, which was 2 meters. So we're going to have 1100 newtons times 2. So that means the work done by Team A is 2200 joules. And that's how we calculate the work. So now that we're a bit warmed up, let's look now at question 13. So a fighter jet is launched from an aircraft carrier with the aid of its own engines and a steam-powered catapult. Okay, so it's sort of taking off, but it's getting a catapult to fling it forward as well. Now, the thrust of its engines is 2.3 times 10 to the 5 newtons. Alrighty, that's very good. Now, in being launched from rest, it moves through a distance of 87 meters and has a kinetic energy of 4.5 times 10 to the 7 joules at liftoff. So what is the work done on the jet by the catapult? Okay, so this is a little bit interesting. So the thing that we need to take away from this is that what is causing the jet to take off? What's causing it to launch forward? And the answer is the engines, so the jet's engines, and the catapult. Now, recalling as well that any amount of energy that results in a change of movement is work. So we know that the work from the engine and the work from the catapult is going to equal to the change in the kinetic energy. So we're going to have the kinetic energy final minus kinetic energy initial, because that's going to tell us the amount of work that these two did, so the engine and the catapult, that results in the change in motion of the jet as it's trying to take off. So the big thing here, it says in being launched from rest. So we know that the initial kinetic energy is going to be 0 because it's at rest, it's not moving. So we can eliminate this one. Now we have a look through here. So the work from the catapult, that's what we want to find. That's our overall goal. The work from the engine is what we don't know. But we do know the final kinetic energy from the jet. So it moves through a distance of 87 meters and it has a kinetic energy of 4.5 times 10 to the 7 joules. Okay, so what we do here, I'm just going to rearrange this. Now, we know the kinetic energy. We need to find out the work from the engine. So remember, work is equal to force times displacement. So we know that the thrust of the engine is going to be 2.3 times 10 to the 5, and we know that it's covering a distance of 87 meters. So we're going to have the work from the catapult is equal to the final kinetic energy, which, as it says here, is 4.5 times 10 to the 7 joules minus the work done by the engine. So the force, which is 2.3 times 10 to the 5 newtons, multiplied by the distance or displacement, which is 87 meters. So that means that the work by the catapult is going to equal 4.5 times 10 to the 7 minus everything in here, which is going to give us a total work of 2.5 times 10 to the 7 joules. So again, in terms of raw calculation, this question wasn't too bad. The hardest part was that we were given so much information and just being able to understand what to do with it. So again, if you're struggling to start questions like this, I highly recommend you go back to video 1 and make sure that you understand what work is, what kinetic energy is, and that will help you to extract that key information and solve questions like this. Okay, so let us look now at question 17. So, a water skier is being pulled by a tow rope attached to a boat. Okay, sounds like fun. So as the driver pushes the throttle forward, the skier accelerates, naturally. So we've got a 70.3 kilo skier. He has an initial speed of 6.1 meters per second. So later that speed will increase to 11.3 meters per second. So we need to determine the work done by the net external force acting on the skier. So we need to find the work done by the boat, in other words. So, remembering that work results in a change in movement, which is what we're seeing here. So we want to see work is equal to, now this isn't going to be force times displacement, because we're seeing that it's going to be a change in the speed. So it's going from 6.1 meters per second to 11.3. So we're seeing a change in the kinetic energy. So remembering that kinetic energy is equal to 1/2 mv squared. So we want to look at the kinetic energy final minus the kinetic energy initial, because the difference in the initial and the final kinetic energy will tell us the amount of work that the speedboat did. So, work is equal to... So now we just plug in all of our values. So work is equal to 1/2 the mass, which is 70.3, multiplied by the final velocity, which is 11.3, minus 1/2 70.3, multiplied by the initial velocity, which is 6.1 meters per second, squared. So all we have to do now is punch this into our calculators. So 1/2 of 70 is going to be 35.15 times 11.3 minus 35.15 times 6.1 squared. And that will give us a total work of 3.2 times 10 to the 3 joules, meaning that it took 3.2 times 10 to the 3 joules to accelerate the skier from 6.1 meters per second to 11.3 meters per second. Okay, so now let us have a look at question 77. So, a 2 kilo rock is released from rest and has a height of 20 meters. Now, ignoring air resistance, determine the kinetic energy, potential energy, and total mechanical energy at each of the following heights. So at 20 meters, 10 meters, or 0 meters. Okay, so this is where things get a little bit interesting. So what we need to do is, we're missing a bit of information. Because in order for us to calculate the kinetic energy, we need to know its velocity. Now this is hard because how do we know the velocity at each of these 3 different points? So what we can do is, because again there is no reference to time, we can use the formula v squared is equal to VO squared plus 2AX. Now, because we know that the initial velocity is going to equal to 0 meters per second, because it's starting from rest, we know that the acceleration is 9.8 meters per second squared, because we're dropping the stone. So what is the go with the displacement? So this is where it gets a little bit tricky, because the height and the displacement are opposites. Because if you think about it, if I've got a stone, and I hold this stone above here, it has a height of 20 meters. But its displacement is 0, because it hasn't moved anywhere yet. Whereas if I dropped the stone, so if I drop the stone, it goes thunk down here, its height is equal to 0, because it's down here, but the displacement is 20 meters. So the displacement and the height are inverse to each other. So how we can get around that is, we know that the displacement is going to be 20 meters minus whatever height it is. Because as the stone has let's say a height of 2 meters, it must have traveled 18 meters to achieve an overall distance of 20. So because we know that the maximum it can fall is 20 meters, we know that if we just subtract the remaining height from 20, that will give us how far the stone has fallen. So if we look at our equation here, so we've got v squared VO squared plus 2ax, knowing that the potential energy is mgh and the kinetic energy is 1/2 mv squared. So we know the height, because we're given it here. We know gravity, we know the mass, so we need to find the velocity squared. And it so happens we have velocity squared right here. So we can go velocity squared is equal to the initial velocity squared, which is going to be 0 because it's at rest. So we've got 2 times a times x. But remember, x, we are substituting with this, but it's because we know that the displacement is going to be changing depending on the height. So we know that v squared is going to equal to 2ax. Now we can substitute this into our kinematic formula over here. So that means we're going to have the kinetic energy is 1/2 of 2a, 20 minus h, times the mass. Now because we've got 1/2 and 2, they can cancel, because essentially what it's doing is it's doubling and then halving itself. So these will cancel each other out, which means that we're going to have our final equation, which is going to be mass times the acceleration times 20 minus the height. Okay, so let's now apply this. So let's look at when the height is equal to 20 meters. So when the height is equal to 20 meters, it means they haven't dropped it yet. It's at the very, very top. So the kinetic energy is going to equal to ma times 20 minus h. So we're going to have the mass, which is 2 kilos, times the acceleration, which is 9.8 meters per second squared, multiplied by 20 minus h. So because the height is 20, we're going to have 20 minus 20, which is going to give us 0. So 0 times 9.8 is 0, times 2 is 0. But this makes sense, because if we're holding the stone and we haven't dropped it yet, then its kinetic energy is going to be 0 because it's not moving. So that's good, that makes sense. So that means that our kinetic energy is going to equal to 0 joules. So, we've got kinetic energy. Let's look at potential energy. So, potential energy is equal to mgh. So the potential energy is going to be the mass, which is 2 times 9.8 meters per second squared. That's the acceleration, multiplied by the height. So the height is 20 meters. So that means that we're going to have 2 times 9.8 times 20. So that's going to give us the potential energy of 392 joules. So now we look at the height when it's equal to 10 meters. So kinetic energy is equal to mass, acceleration, 20 minus height. So it's going to be 2 kilos multiplied by 9.8 meters per second squared, multiplied by 20 minus the height, which is 10 meters. So 2 times 9.8, that's going to give us 19.6, and we multiply this by 20 minus 10, which is 10. So that's going to give us a kinetic energy of 196 joules. So now we look at our potential energy. So the potential energy is equal to mgh. So potential energy is equal to 2 times 9.8 multiplied by the height, which is 10 meters, which is going to give us a potential energy of 196 joules. So now we look at our final one where the height is equal to 0 meters. So kinetic energy is equal to 2 times 9.8 times 20 minus 0, which means the kinetic energy is going to equal to 2 times 9.8 times 20, which is going to give us 392 joules. Then we look at the potential energy, which is the mass times gravity times the height, which is going to be 0. So the potential energy is going to equal to 0 joules. So now to finish off this question, we need to look at the total mechanical energy. So the energy total is going to equal to the kinetic energy plus the potential energy. So when the height is equal to 20 meters, we have the kinetic energy plus the potential energy. So that's going to give us a total mechanical energy of 392. Then we look at when the height is at 10 meters. We're going to have 196 plus 196, which is 392. And we look at our final one, which is going to be when the height is equal to 0. So again, 392 plus 0 is going to give us 392 joules. And this again further reinforces the law of conservation of energy in that it doesn't matter whether the stone was at the top or at the bottom, it is only the change of gravitational potential energy to kinetic energy, and that no energy is being created or destroyed.